development and emergent materials. His research interests involve femto and sub-femtosecond dynamics of nanoscale atomic systems, nanoscale superfluid systems, extreme UV physics with synchrotrons, and tabletop laser sources. And he's been involved in technologies related to the development of photonic devices and photolithography at various scales, both deep UV and extreme UV wavelengths. And he's very passionate about combining physics, photonics for both scientific education and research. So we are glad to have Professor Ramakrishnan with us for this webinar. And over to you, Professor Shivaram.
Thank you, Professor Shankaram. It's indeed both a pleasure and an honor to be presenting this webinar, both from the perspective of the kind funding that the ANRF, formerly SCRB, DST, and Ministry of Science and Technology at large for especially the foundational science research, which motivates much of this talk, as well as to my own home institute, the Indian Institute of Technology Madras, who have also equally funded this research in the sense of promoting academic research and basic science, applied science, and technologies, all of which we will see are a part of this talk. And the Industry Consultancy and Sponsored Research Office, along with the Global Engagement Office, for giving me this wonderful opportunity to showcase both our work and but I will present in a much broader context that of an ultra-fast quantum world, this wonderful science that I am very passionate about and keeps me and several others ticking busy both in the day and sometimes even in the nights. So in this seminar on ultra-fast atomic relaxation dynamics in quantum aggregates, I will use prototypical systems to, as I said, showcase this entire field of quantum dynamics, experimental quantum dynamics, that is, which we perform from the shores of this beautiful historic city, Chennai. If you are in the audience and probably not Indian, you might not be immediately aware where this is located in the peninsula. It's on the eastern coast and the oldest modern city by some definition, and the home of wonderful monolithic structures as that we see in the background, as well as of India's shining university, where I'm fortunate to be associated with as a faculty, the Indian Institute of Technology Madras, a shore of a wonderful seashore and green and exquisite flora and fauna, such as the spotted and other deer, which are the denizens of our Sylvan campus, and also on another end of the spectrum, the research park for translational research. So it is nature, natural sciences, and technology all amalgamated in one, home to more than 15,000 students and continually ranked among if not the top technical university of India, home also to roads like the Bonn Avenue, reminiscent of the generous German seed funding, which brought this technical institution up in this green garden, where also the Delhi Avenue meets the Bonn Avenue at the Elephant Circle. So for more, you will have to visit us. So with that preamble, the outline to my talk is essentially as follows. I hope to, through this talk, not just showcase snippets of our research, but also for a broader, especially student audience, especially Indian student audience, if not more, present an invitation to the ultra-fast quantum world, and then delve into my own interest in this helium nanodroplets, which we will find out what they are, and correlated electron dynamics and collective phenomena in these exotic yet amenable quantum system, how we play with them, how we are intrigued by them, where we present scenario where even 2 electrons may be too many, as well as we showcase that we also have the ability to handle too many electrons and image these systems when they evolve fast. But let's take a step back and ask, what do we mean by ultrafast and what do we mean by the ultrafast quantum world? Ultrafast phenomena are no stranger to human curiosity, science, and technology, particularly the galloping of a horse, which in the 1800s led to the genesis of this field from the perspective of experiments and technology, when Leyland Stanford threw a bet asking whether we can confirm through direct means, not by conjecture or fantastic theories, equations, or whatever it might be, but in the sense of seeing is believing, whether at any point of time during the galloping of a horse, all four of its hooves leave the ground and it is entirely sort of hung in air, right? Even in this in one of the earliest pictures of ultrafast videography, which Muybridge successfully cracked. So this is millisecond ultrafast phenomena, where you can, in one of the snapshots, see that all the four groups indeed lift off from the ground. Now, from the gallop and motion of atoms to the world where these similar questions can be asked and answered about molecules, which heralded the Nobel Prize in 1999 in chemistry, to Ahmed Zuel, which also heralded the field of ultrafast dynamics, and experimentally observing various phenomena, to the first decade of the 21st century, which saw atoms being imaged and electron dynamics in them on sub-femtosecond or attosecond timescales, in very similar spirit about the how electrons gallop and take shape during their motion, as well as nanoparticles and so on. So much so that this science has kept us both intrigued and busy all the way from early or pre 2000s onwards, such that a Nobel Prize almost every 5 years has gone on to be given to one of the pioneers in this or a related science. I'm not capturing all the prizes. I'm capturing the what could be thought of as the first in the series of prizes, and the most recent in 2023 to the pioneers of sub-femtosecond or attosecond physics. So therefore, while Feynman said that there is plenty of room at the bottom, that is on the nano and even sub-nano or angstrom scale, we may also recognize in this case that there is not only plenty of room, there is plenty of room and time at the bottom. So now, one of we are kind of fortunate, and I am lucky to be doing this in 2026, because I don't need too much more of a motivation to present this science and technology that goes with it, because the Nobel citation of 2023 in physics reads that these three pioneers, Lullier, Krauss, and Agostini, were awarded this for methods that generate attosecond pulses of light for the study of electron dynamics in matter. So that's maybe good enough, but what do they exactly mean? Let's take a step back and ask, what do we mean by ultrafast? And it seems that the word atto, which is 1,000 times smaller than the prefix femto, um, has intrigued even the Nobel Committee and its eminence. So, what is an attosecond? So, if we put the heartbeat, which is approximately 1 per second for humans, at the center of this linear scale, or it could even be not linear, but maybe logarithmic scale, but it's right there, then the age of the universe in terms of the number of human heartbeats would be 10 to the 18 seconds or 10 to the 18 durations of a human heartbeat. It's that long ago, right? And likewise, the phenomena that we can control and observe in a laboratory, the shortest time span on which clocks can tick for us in order to measure such phenomena lies on the other end of the scale at 10 to the minus 18 of a second or of a heartbeat. So that's the magnitude of difference in terms of the heartbeat. Of course, it's a remarkable achievement for human species that the same sort of community of say physicists, chemists, engineers, and biologists can study phenomena all the way from 10 to the minus 18 to 10 to the plus 18, 36 orders of unfathomable magnitude, right? So take a second, let's take a second and feel it, feel the beat, so to say, right? And a nanosecond is indeed that, but also from a very sort of intuitive perspective, high school physics or undergrad physics perspective, what is a nanosecond? We can place this time scale on some very primordial details of the simplest of atoms, which is the hydrogen atom, whose electron, so in the sense of a planetary Keplerian analog, circumambulates the proton, which is the nucleus, which is much smaller than the trajectory of the electron, with a velocity which is essentially the speed of light, or the in vacuo speed of light, divided by 137. So alpha, the fine structure constant, which is beautiful number, constant and constant in this universe, essentially multiplies another beautiful constant, which is the in vacuo speed of light c. That's the velocity of the electron. You don't need to solve too many equations for this. You can essentially sort of deduce this even before one solves sophisticated equations in the back of an envelope. As we can also the Bohr orbit of the electron, which is the radius, which is about half an angstrom, translating to a circumference of about 3 angstroms, an angstrom being 10 to the minus 10 meters. So this electron, if it were to be a planet, analogous planet moving around a star, which it is not, it is a quantum object, but then it is a very good analogy still, would complete one circumambulation, which is what the Earth does in 1 year, in a time scale which is about 150 attoseconds. Okay, so that puts something in perspective. Something in the motion of electrons and atoms happens on this time scale. Okay, let's take one step deeper and further and look at one of maybe the 5 most important equations, or even the 3 most important equations in all of physics, the Schrödinger equation, which has wrapped in it all phenomena of the quantum world, be it superposition, be it tunneling, be it entanglement, whatever else, right? The Schrödinger and its family of equations, could be Dirac, could be whatever other formalism of quantum mechanics, all of which are very related and in many cases even equivalent, is captured in this equation, which to a scientist or engineer would remind us of the heat diffusion equation, where we have the second derivative in space, and the right hand side would also be a first order time derivative, which I haven't written just to keep things simple. But then, in order to solve this so-called problem of the hydrogen atom, often done in undergraduate and master's level physics textbooks, which only need you to know calculus and differential equation solving, lead us to the fact that we need to solve for this wave function, or the solution, which is psi, and one needs to proceed further. So we insert a potential. R is the radial variable. For the physicists in the audience, of course, this is quite trivial to see, and we need to solve this equation. But of course, we are not going to solve this equation in this limited lecture. It would take us the major part of an undergraduate quantum mechanics course to do it. But in the spirit of Dirac, who said, I consider what I understand when I predict things without solving it. Of course, it's possible for a great man. In fact, on the chalkboard here, he is writing down something about the hydrogen molecule, as we can see, but we are talking about the atom here. But then from this equation, here H, or H bar, is the Planck's or reduced Planck's constant. M is the mass of the electron. E is the electronic charge of the electron, which is an atomic unit of charge in itself. E being the possible, from this equation, evidently the eigenvalues or the allowed energies in this problem. So the natural time scale for this problem is set by deducing a time which I can simply put together using dimensional analysis by combining M, H, M, E, and possibly the sort of epsilon naught, which is the permittivity of free space, which comes into the system of units that I'm using. And the velocity of the electron was the in vacuo speed of light divided by 137. So I can construct an energy by using the very famous equation mc square is energy. Right, so put that over here. That's the energy of the electron, and I know a relation that is of the type that E times T, energy times time, is the Planck's constant. So I'm giving you a sort of shortcut of how to get quickly to a time scale based on just these constants h, m, e, and epsilon naught, which I've borrowed. This quantity plugging in for h, m, e, mass of the electron, mass of the electron m, e its electric charge, h or h bar the Planck's constant or the reduced Planck's constant, and the and epsilon naught being put into this equation give us a time scale of 24 attoseconds. Again, 24 times 10 to the minus 18 seconds. Once again, this manifests in our discussion. So there seems to be something important to this. In fact, this is one atomic unit of time. If E, the electric charge, is one atomic unit of charge, M, the mass of the electron, is one atomic unit of mass, and H would actually be an atomic unit of a quantity called action. So this then becomes naturally an atomic unit of time. So an attosecond is an atomic unit of time. In layman's sense, this is like the heartbeat of the electron. Electron dynamics takes place on this time scale, much as human dynamics takes place on the time scale of a second or so. Now we can go a step further, and I'm just taking a bit of liberty here to solve the eigenvalue problem and superpose two levels in the hydrogen atom, the 1s level and the 2p level, which are then coupled by some sort of electric field, forming a sort of superposition of two states in the presence of an electric field. And sorry, just a second. And what you see as the red moving blob, the red blob that is oscillating on the right half of this screen over here, where my cursor is also hovering, is the probability density of finding the electron in this system. And you can see that there were some, nice looking motions of these balloon like structures. So, which was the probability density of the electron, which is some kind of oscillation that is taking place. Again, now the time period of that oscillation, I will not dwell too much upon how the math involved is essentially turns out to be 400 attoseconds. So the atto or 10 to the minus 18 scale comes into living in terms of the dynamics of electrons. So that essentially is the core of the ultrafast world, that we need to look at electrons on timescales of atto, femto, and picoseconds. In other words, electronic dynamics takes place on sub-femto or attosecond timescales. Vibrational dynamics in molecules takes place on femtosecond timescales. This is what gave the Nobel Prize to Zevel. This was the Nobel Prize to Agustini, Krauss, and Lullier. In between, there was a Nobel Prize in 2018 to Strickland and Maru for coming up with laser technologies that enable this. And of course, there's another kind of motion in molecules which have more than two atoms, which is rotation. Rotations take place on picosecond timescales, and of course, in condensed phase phonons, all the way going up to nano and microseconds, and so on and so forth. So these are atomic processes. Okay, with that preamble, now, having set the stage, let me present some of my work, and in the process thank my collaborators, all of whom without have contributed it, and without all of whom none of this work would actually have been possible. My colleagues from overseas centers, especially my long-term collaborator, Professor Marcel Mudrich, and his team, Professor Taif Ben Al-Taif, both from Aus University, Professor Pfeiffer and Mosammer from Heidelberg at MPIK, Professor Stinkermeyer, Professor Laforge, Professor Sura, Professor Kovachev and Mogner, Professor Richter, whom unfortunately we lost last year, Professor Caligari, Prince, Professor Coreno, Simone, O'Keefe, Catone, Zima, Tocini from the electrosynchrotron, and my colleagues, my current and former students at IIT Madras, Dr. Shubhendu De, who is now in Sorbonne University as a postdoc with Professor Sisura, Keshav Sishodia, who will graduate soon, Professor Vandana Sharma in IIT Hyderabad, and our co-jointly guided student Shanket Sen, who's also in France at the Soleil Synchrotron, and Sudha Mandal, who's now at Paul Scheller Institute in Villigen in Switzerland, Professor Bapat, Arnab Sen, Professor Krishnamurthy, and Professor Ram Gopal, and the funding agencies in India and abroad. So, helium nanodroplets, what are these which I brought up early on? So, helium nanodroplets are weakly van der Waals bound aggregates of helium atoms. So these essentially are a unique system in which helium atoms are put together in a sort of van der Waals bound aggregate. We will look at this a little deeper. So these are in the context of an Indian audience. These are like laddus of helium, except that they are not really a solid mass. They are a superfluid. They have an internal temperature of zero point 0.4 Kelvin, 400 millikelvin. Then the lambda point of helium is 2.1 Kelvin. And since these are below the lambda point of helium, they are naturally superfluid. They are also ideal spectroscopic matrices in the sense inside these clusters, or what I call laddus colloquially, we can dope other atoms of molecules or molecules and form an ideal spectroscopic matrix, owing to the fact that here helium, which plays then the role of a solvent, has a large transparency window going all the way up to 20 eV into the extreme ultraviolet. And in the process of getting doped, aggregates that are formed inside helium droplets are sympathetically cooled to the temperature of the droplet itself. So they are just sticky enough, yet they don't interact too much that these dopants are significantly affected in any way, thus becoming nanocrioreactors for studying nanoscale and angstrom scale aggregates. So, how do we make these helium clusters in the lab? So, these are formed by pushing high purity helium gas through a nozzle whose body is usually made of copper, and an orifice which is a 5 or 10 micrometer hole drilled onto a platinum film, both of which are attached. And the nozzle itself, the copper nozzle's temperature is varied between 5 to 30 Kelvin, and the pressure of the helium gas is held to something like 50 to 100 bar behind this nozzle, and the jet that comes out of this orifice is then passed through a shaped a hole here, which is called a skimmer. This extracts the cold part of the jet and sends this across to the next chamber, where we can essentially use pickup to dope the helium that has come out now from the nozzle and form these nanodroplets, aggregates, or what I call laddus. And in the doping cell, we can hold dopant atoms or molecules in a vapor state. If there is sufficient vapor pressure at room temperature, just hold it at room temperature. If not, heat this cell, making it a little oven for dopants, which we typically do for metals, and some dopants which are in solid phase at room temperature. So the jet that passes through this beam, which is actually flying at supersonic speeds, essentially then, and containing these superfluid helium nanodroplets, then captures some of the dopant molecules or atoms from the vapor, and they stick onto it almost once again, like it happens in the case of Indian deserts, right? So in this beam, we then have helium clusters or nanoparticles typically, whose size distribution is not very, sharply peaked at any point. It's log normal. So the width of the distribution, delta n, is of the same order and very similar to the mean size of clusters in this distribution. Its density is liquid-like, 10 to the 21 per cc, and we can vary the size of these helium clusters from all the way from sub-nanometers to even several hundred nanometers by a very fine knob, which is the temperature of this nozzle. This temperature can be regulated using a very fine PID controller, which is what we usually do in the experiment. And the setup looks a bit like this. I will dwell a little more on the setup in the next view graph. So now when these superfluid helium clusters pick up atoms or molecules, what happens to the dopants? Where are they, inside or on, even on these helium clusters, right? So in order to determine that, and which has already been done, studies have shown, especially laser spectroscopy, that rare gas atoms essentially are dissolved and are held inside the droplet, whereas alkali atoms attach to the surface of these droplets. Alkaline earth atoms such as calcium, magnesium, barium, and others are held beneath the surface layers. So I call rare gas atoms, actually also rare gases and molecules are basically diverse. They've gone into the ocean or into the liquid, whereas alkali atoms are floaters. They kind of swim on the surface, whereas alkaline earths are like snorkelers. A more rigorous sort of analysis captured by the Anceloto parameter is here for you to see, but very much a little bit beyond the scope of this talk in terms of time. So I move over. But then let's pause for a moment here and acknowledge the following fact. Superfluidity, what is that? This GIF, if you observe carefully, presents to you the world of superfluids. This is helium, that bosonic helium-4. Helium has two isotopes, helium-3 and helium-4, which are held in, both of which can be found in nature, but the more abundant it is, of course, helium-4. Now you see that the helium liquid here is dripping. So why is it dripping? Is there a hole in the cup? No, there's no hole in the cup. This superfluid, simply because of the way it interacts with the walls, creeps along the walls of this container and flows out. So this is like taking a cup of coffee, right? And then finding that no matter what, even if the cup is only half full, coffee starts to overflow from the sides. If this happened to me in my office, or you where you are, you would be spooked, right? This would be like a paranormal phenomenon. No, in the quantum world, nothing is abnormal, right? Or paranormal for that matter. Superfluidity is a macroscopic quantum phenomenon. And this has been studied by several Nobel Prizes, all the way from one of the very early ones to Camerly Onus, who discovered who basically liquefied helium and therefore paved way for us to study this macroscopic phenomenon in the quantum world. Helium-3 superfluidity was recognized with Nobel Prize in '96 to Lee, Osheroff, and Richardson. And in 2003, one of the pioneers of macroscopic phenomena of the quantum world, Sir Anthony Leggett, eminent physicist, whom very unfortunately we just lost. And just yesterday, his obituary was published in Nature, one of my scientific heroes, undoubtedly, who also made the proposal for the most recent Physics Nobel Prize given in 2025 to Clark, Devore, and Martini for macroscopic quantum tunneling phenomena. This is indeed a very fascinating world. So therefore, in our research, we combine the ultra fast world and its fascinations with the intrigue of the quantum world and even the macroscopic quantum world. So it is indeed a study of ultra-fast quantum phenomena. So superfluidity is in helium droplets was even on the nanoscale was evidenced by looking at the infrared and rotational spectra of OCS, a linear chain molecule, OC and S, um, in the infrared spectra of this particular molecule by looking at the P and R branches in helium droplets. The IR spectrum in these panels over here, but more specifically the top panel here, shows 6 very clear P1 to P3 or 7 very clear spectral lines, P1 to P3, R0 to R3. Whereas the same molecule, when its rotational spectrum is measured um, in the infrared, essentially in helium-3 droplets, essentially shows a very blurred band over here. So this tells us, in some sense, for with spectroscopic analysis, that the molecule is rotating more or less freely, although it is attached to a helium droplet, whereas here it's strongly interacting with the solvent, right? So this shows that molecules in nanoscale helium droplets have nearly free motion. I say nearly because later experiments showed that there is a solvation shell of helium which is coating these molecules, and the whole solvation shell, however, rotates essentially freely in the superfluid droplet. So that is superfluidity. Another manifestation of superfluidity in the macroscopic scale, the Andronikashvili experiment essentially showed that a paddle rotating in a superfluid, albeit immersed in the superfluid, sees no resistance at all from the liquid. There is no friction in the motion. It's also true for linear motion in these in the superfluid, where in some sense there is a critical Landau velocity which exists, which essentially means that if I take a little ball, a bead, or whatever, and throw it in a fluid, and the velocity of this bead is less than 60 meters per second, then it moves through the superfluid unhindered, unaware that it is actually in a liquid. There is no viscosity that it encounters at all. So this is quite intriguing as a macroscopic effect. However, this was of course also worked upon by great people, macroscopic superfluidity in helium by Lev Landau, Richard Feynman, and several others, leading to this dispersion curve of superfluid helium, which of course in the case of nanoscopic helium is not very well established in some sense yet. One needs to investigate that further. But then in a beautiful experiment that took place in 2013 in the group of Marcel Drabels, they posited observing such a phenomenon where even on in nanoscale helium droplets, a velocity limit like the critical Landau velocity exists. But of course, one can also say that this is going to be a matter of further investigation and research. Now, in our own work, what we do is we study correlated electron dynamics in these helium nanodroplets, and I come to that. Here are some associated papers that we have published, often together with the colleagues whom I mentioned. So let's go into helium nanodroplets and see how we measure the electron dynamics uh, in these helium nanodroplets themselves. So as I said earlier, helium nanodroplets are produced using a cryogenic copper nozzle from which pressured helium gas is made to squirt out a high pressure, 50 to 100 bar, and through a tiny nozzle, say 10 micrometers, and from this come out droplets of helium. They are actually not coming out always from the liquid phase in the nozzle. They often are in the gas phase while the gas comes out and expands. Due to the expansion, there is cooling which is actually non-adiabatic here, so it's not really the kind of cooling that we usually expect under gentler conditions. But then there is aggregation. This is a whole science in itself. But we extract the cold part of this jet in a skimmer and go to the next vacuum chamber. The first chamber where we produce these helium clusters is what we call the source chamber. And then here we have the doping chamber. And in the doping chamber, we have a chopper which chops the beam to periodically block it and let it through. This is for making measurements with and without these droplets. It's a matter of technicality. So if this you find it new or overwhelming even, please ignore that. Then the jet of helium clusters is then passed through a doping cell where the dopant vapor is shown here as a red gas. Some of it gets attached to the helium droplets, and we once again pass this jet of doped helium nanodroplets to the next and final chamber where the actual action of the experiment occurs, which we call then the spectrometer chamber, which is over here. And in this spectrometer chamber at nearly its geometric center, in our case, we come with extreme ultraviolet synchrotron light, which is focused geometrically to the center of the chamber axis, also the spread of the beam to the center of this helium droplet beam. And here helium clusters, almost always just one cluster per synchrotron pulse interacts with it at a time. And here we are interested in photoionization event. In a photoionization, as we know, electrons are removed from atoms, molecules, here clusters, or it could be condensed matter. For us here, it is helium droplets. So when extreme ultraviolet light is incident on these droplets, we essentially have, depending on the energy of the photon or its frequency, either one or two electrons in from a helium atom removed, right? So then we have two kinds of outcomes of products from this photoreaction. One are electrons. So the electrons are pushed downwards in this spectrometer, and the other are ions. Ions are pushed upwards in this spectrometer. At the top, at the ion end of the spectrometer, we have a detector which is sensitive to measure ions, often a multi-channel or micro-channel plate detector which detects the ions and discriminates them by their flight times. The flight time of an ion measured in this spectrometer is proportional to the square root of the mass by charge of the ion. So if it is proton H plus, you essentially then have a particular time of flight. If you have helium plus, the mass of a helium ion is 4 units, 4 atomic units. Its charge is 1. Therefore, the flight time of a helium ion would be twice that of a hydrogen ion, which is a proton, and so on and so forth. We could have O plus ions, 18 mass 18 ions, which correspond to H2O plus ions, which are also H2O is also present in the residual gas in this chamber, and so on. Matter of technical detail once again. But then the corresponding electron corresponding to this is captured on the other side of the detector using a position sensitive detector. I will have more to say about both these spectrometers in the next view graph. The bottom spectrometer images the electron cloud that is coming out, so it's called a velocity map imaging spectrometer. The top spectrometer for ions operates on time of flight principle, so it's called a time of flight spectrometer. So here in this view graph, it's clear that the red electron ball flies fast and starts a clock. And the ion, the blue ball, is going to reach its detector, and when it reaches the detector, we have a click. So that is how the time of flight of the ions is done. Now, not only can we do this, the electrons which reach the detector, remember I said reach a position sensitive detector. So the red E over here is the red E over here is the electron. It follows a green trajectory and it reaches the position sensitive detector plate, which is like a camera. So electrons with different velocities that they acquire at the time of the photoionization event are then placed different on different velocity or momentum spheres. So let's say a nanosecond after the photon is absorbed, if we look at where the electron is, depending on its velocity, it would have moved away from the center or the position of its parent atom or nucleus to somewhere in the outside on the surface of a spherical shell whose radius is proportional to the velocity of the electron. So this entire momentum sphere is projected through electrostatic lenses and it is projected onto an imaging detector. So when you do this in the context of condensed matter physics, okay, now my animation seems to be working. So the electron is essentially flying away from the axis of the spectrometer. Farther away it is from the axis of the spectrometer, which is the black dashed line, the greater the initial momentum of the electron. So, and we also have angular information here. So this is an angle resolved photo emission spectroscopy system, spectrometer or technique that we are implementing. Now, what we do is we do this in tandem. For every electron that is detected, since the ion, okay, that essentially is related to the birth of this electron also reaches its own corresponding detector and clock, we can perform what is called a coincidence measurement. So photoelectron, photoion coincidence is what we do. Since we image the electrons using this velocity mapping technique, this is the VMI, PICO or PEPICO technique. So VMI PEPICO coincidence spectroscopy is our go-to technique. But for an Indian audience, this is not very new as to understand how the VMI spectrometer works, but because that's what happens in cricket. So the bowler bowls his ball, the batter hits it, there's a deflection, and the slips are catching it, right? So let's look at that once again. So what happens initially, the ball can, then there's a momentum transfer at the bat, and depending on how much momentum is transferred to the ball, the ball either goes close to the wicket keeper, the first slip, second slip, third slip, fourth or fifth, or you can have as many as what 10 or 9 slips a bowler and a wicket keeper in a cricket game, right? So that's a 9 pixel detector. We have many more pixels in a real world detector of this sort. So that's exactly how uh, on that principle the momentum spectroscopy works. However, modern cricket also employs the coincidence measurement where you not only have videographic evidence, but you coincide that with acoustic evidence. Okay, the SNCO or Hawkeye or whatever it's called, we compare video and audio and make a coincidence measurement. So there unbeknownst to us, or without giving it the same name, we are doing a coincidence measurement, and it is obvious to anyone watching this game, for example, which immediately tells us how much advantage coincidence methods present in order to resolve otherwise ambiguous phenomena or observations. So armed with this understanding, let's go and look at what happens to atoms or molecules over here. So atoms essentially, their VMI image looks like two moon halves, and this is a matter of technicality, so I will not go too much into this, right? So we have essentially VMI spectra of electrons on the detector from atomic helium, and look here at helium nanodroplets. It has some similarities but also quite some differences. I will skip the details that are involved in the physics, but this is a very good example of physics, atomic physics 101 being shown in live experiment. Now, helium nanodroplets, when I subject them to these extreme ultraviolet photons, we need to take cognizance of the excitation levels of atomic helium. The ground state of helium is essentially 20 electron volts below the first electric dipole allowed transition when a photon of 22 eV is approximately 22 eV is absorbed by the helium atom. Then there is the 1s, 3p, 1s, 4p, and p, and the entire manifold over here. So now a photon coming here will promote the electron to higher and higher energy levels, and we can perform its spectroscopy. So now if I now take helium nanodroplets instead of atoms and then sweep the photon energy from between 20 to a 26 eV and collect the electrons and ions that emerge out of this photoreaction, whereas for atoms, one would have to exceed the atomic ionization threshold of 24.6 eV in order for the electron to come out of the atom and reach our detector. For helium droplets, already at about 23 eV, electrons start coming out. So this is the electronic structure of a part of the electronic structure of helium nanodroplets. One can also collect photons while exciting this system electronically. The fluorescence photons, if collected as photon energy is swept, present the complementary picture. We see a huge amount of fluorescence between 20 and 22 eV, also 22.5 eV. So this tells us the other part of the electronic structure story, that there is a nice bound transition in helium nanodroplets occurring when excited between about 20.5 eV to 22.5 electron volts. So these two together present a combined picture of the electronic structure of these droplets. In the first region below 23 eV, we have only excitation. In the second region, we have we have excitation plus some ionization, and the third region, about 24.6 eV, is dominated by ionization for both atoms and clusters. So armed with this, I would like to showcase the first story of dynamics in these droplets, which was performed by my collaborator, Professor Marcin Muric, and colleagues, where they excited these helium droplets with an XUV pump pulse from a free electron laser called Fermi at Trieste on the Adriatic coast in Italy. And then they used another pulse which was delayed, a UV probe pulse with a photon energy of about 3 electron volts. Okay. So now what did they do in this experiment? They used the pump pulse from the free electron laser Fermi to promote electrons to the top of this fluorescence band, which is the first, you can say, optically allowed set of transitions, a band of excitations that can happen in this droplet. And then they came, there could be interband relaxation, we will see about that, but then they came with a UV probe pulse, right, whose energy could be 3 eV or 4 eV depending upon what it is, but it is of course ultraviolet, which is enough to promote the electrons and throw them out of these bound states of the atom or the droplet, right? And in the process, owing to the photoelectric effect, the electron comes out with a certain kinetic energy, which is essentially the energy of the UV photon plus the energy of the state where the electron lives, less the ionization energy of the helium atom. Okay, so from that kinetic energy we will be able to discern where the droplet was as a function of the delay time between the exciting pump and the UV probe. So this was performed, and you can see on the horizontal time the delay in the so-called pump probe time. The electrons were initially at very early times close to t is equal to 0. Electrons came out with the highest kinetic energy, and then for later delay times they essentially the energy started decreasing. It means the electron which was excited has started to perform this intraband transition going to the lower parts of this band, and here close to the 1s3p band the electron seems to be living forever. This contour flattens out here. Okay, so there is no further dynamics, it seems. So that is well known because the 1s 2s state in helium is known to be metastable. But meanwhile, computations performed by the group of Manuel Barranco in Barcelona, here treating a helium atom like that of an electron and doing density functional theory, shows that this excited helium literally literally lives in a bubble, right? This animation will show you. So essentially, the yellow is the excited electronic density of the excited helium atom, and you can see how this nanoscale bubble, this droplet itself is about 10 nanometers wide. So the bubble is like about a nanometer or so in diameter, if I can ascribe such a quantity. And this bubble has essentially, is moving around in the superfluid and doing very interesting dynamics in the in this inside the droplet. The greater details of this work can be found in this NatureCom paper in 2020. So we know this, and of course, in collaboration with Marcel, we did several experiments. So we have correlated two electron dynamics in helium nanodroplets, which we studied. Now, in this case, one short story that I will present, we come in with photons of 45 electron volts in energy. So 45 electron volts is higher than the ionization energy of a helium atom over here. So obviously, when this photon is absorbed by one of the atoms in the helium nanodroplet, we create a helium ion, helium plus, and an electron which is essentially out from its house, a free, nearly free electron, which is no more bound to its parent atom, which the atom itself from which the electron was removed is a part of this cluster community. The cluster is about 10 nanometers in diameter, right? So very simple physics, just that the energy of this electron would be governed by the photoelectric effect equation, h nu, the photon energy, less the ionization potential of the helium atom. And in this case, this energy h nu less the ionization potential of the helium atom is about 20 electron volts, right? So when the energy of the electron is about 20 electron volts, it can collide with one of the other helium atoms, which is in this community of clustered helium atoms, excited from the n is equal to 1 to n is equal to 2 excited level. And then after this scattering event, it pretty much has no more energy left to any of the atoms, and it will eventually come out of the droplet. So one inelastic scattering event can happen when we take photons of energy greater than 45 eV, it could be 50 eV, it could be 60, 70, whatever. This kind of inelastic scattering process can happen, right? So this is a secondary process in helium droplets. Now, we did this sort of an experiment taking 55 eV photons into consideration. 55 eV photons cannot be produced until about recently using tabletop lasers. Prominently, we get these very easily done at synchrotrons, so which is what we did. We did this study at the electrosynchrotron in Trieste in Italy. So we took small helium droplets, size of about 2 nanometers, about on an average 700 helium atoms per cluster, and then measured the photoelectron. So this is a typical velocity map image. Now the polarization direction of the synchrotron is like this, kind of diagonalish on the screen, and therefore you see these kind of crescent-like structures, which if you pay close attention, are also present in the first BMI image with atoms and also helium droplets, which I showed you. Okay, so this tells me that most of the electrons are coming out with a kinetic energy of 55 minus 20, let's say 25 eV, so nearly 30 electron volts of kinetic energy. Okay, now we increase then the cluster size to 5 nanometers, and these 5 nanometer clusters contain about 11,000 helium atoms. The nozzle here has was maintained at 15 Kelvin, which is a matter of technical detail. Now, in the same velocity map image, done in the same spectrometer, just cranking down the nozzle temperature, increasing the size of these droplets to 5 nanometers, we see further more features over here. We see, first of all, a dot right at the center of this velocity map image. We do see the same outer circle, but then we also see a sort of inner circular ring over here, which means we have three families of electrons coming out of these larger clusters, right? And this spectral feature, which I marked by B over here, is due to the inelastic scattering process that I've shown here, right? And now next, we increase the size of these droplets even further, 40 nanometers. The central dot remains. We see now a feature, the feature B. Let's take the 48 nanometer case, which is the largest droplet that we investigated, right? We have three features: A, the B feature here, which is here, and the C feature here, which is also present. Let me use now the laser pointer. Okay. Okay, PowerPoint allows me to use only the hand icon for this. So this is due to direct photoelectrons, ionize, come out, no inelastic scattering. B is due ionize, undergo one inelastic scattering and come out. What is the feature C? Right. So this is the question that we asked ourselves then, and we now know the answer. The feature C corresponds to electrons coming out with a photon kinetic energy of 15 eV. This is due to a process called interatomic Coulombic decay. I will show the mechanism in a bit. So this comes about from in these large droplets owing to the following process. The process is as follows. So initially, when the 55 eV photon was absorbed by the atom, you created an electron, removing it from the parent. It inelastically collided with another helium atom, exciting it. Then this freed electron with now reduced kinetic energy than it had when it just went away from its parent atom is still in the field of this attractive field of this ion, although it is having enough energy to be free outside from home. This is a little bit like what happens in human families too. So this is the child, this is the parent. The child grows up, okay, becomes financially independent of their parents, and then usually tends to, go around the society, the country, even the world, right? But once in a while, or for whatever good reason, often tends to come back to its native, one of its native places or wherever it settles down. So in this analogy, it's maybe the same native place, and it recombines with the parent ion. Okay, so when it recombines with the parent ion, it is more likely that it recombines as the electron recombines in the excited state of helium, thus creating two excited heliums over here. Recall also in the Moodrich experiment, they showed us that these excited helium atoms do not stay in one place in the droplet. They keep moving around in the superfluid. So at some point, they can even come together and coalesce, as shown here in this view graph. Okay. So when they coalesce, we have two excited helium atoms. The excitation energy contained in each of these excited atoms is about 20 eV. So if you put these together, it is 40 eV, which is greater than the ionization energy of atomic helium. Therefore, there could be then a process where this combined energy budget of 40 eV can be used up for one of the electrons from the excited pairs to go out, which is what happens. So 40 minus 24.6 is about 15.6 electron volts, which is the interatomic Coulombic decay process. It is interatomic because it's happening across two atomic centers. It is Coulombic because the interaction is Coulombic. It is decay because essentially the one of the electron comes up. Okay? So we studied this in greater detail and studied the dynamics too with a high resolution spectrometer, discerning its features. Together with El Taif, my students, Keshav Sishodia, Shuddha Mandal, also from IISA Pune, Shubhendu Day, we together with our collaborators published this nice paper in Physical Revelators in 2023. So this is how the experiments are actually done in real life. This is Marcel, this is Keshav standing on top of this instrument. So you can put a size scale to where these measurements are done. And this is at a world-class synchrotron facility, Electra in Trieste, and quite a challenging experiment in itself, which was done actually during the pandemics. This is the product of pandemic work. Once again, we are sort of proud of the fact that we made good use of this time, and I really thank Dr. Robert Richter, who's no more, unfortunately, with us, and in the process also pay an homage to him through this presentation. So let's move on to the next story in this entire milieu. In the interest of time, I've described all this well enough to the current audience. Okay, so can we track the dynamics of this experiment? I will present this and the next short story in ultra short time scale since we are running out of time. So Keshav decided to track the dynamics of this ICD process using a nanoplasma fluorescence process, in which we essentially made the helium nanodroplets, but then we used a pump pulse, which is an extreme ultraviolet pulse, this time not from a free electron laser, but from a tabletop high harmonic generation source. The probe was a very intense infrared pulse. So the pump was an XUV pulse with an energy of about 50 EV or so, or whatever is stated over here. And then the probe pulse was essentially a intense infrared pulse. So long story short, what the probe pulse did was essentially to use the fact that we have an excited helium atom in the droplet and drive it into a highly ionized plasma state. In the highly ionized plasma state, there's a lot of recombination that can take place within this nanoscale plasma. This nanoscale plasma is again just a highly ionized state of the droplet. The recombination fluorescence lines for the cluster beam are shown here. These are the vertical streaks. This is the corresponding atomic spectrum showing, essentially displaying the resolution of the XUV fluorescence spectrometer. The delay between the exciting UV pulse and the probing intense infrared pulse gives us a signature of the dynamics. The same fluorescence spectrum from two species, the fluorescence from excited helium star, which is neutral excited helium, and helium plus star are both shown here. We use all these lines to track the dynamics. So the dynamics of the fluorescence as a function of droplet size from 5 to 17 nanometers is shown in this view graph. And we can see that there is a step-like feature, there is a plateau, and there is a decay. So this can be modeled using this kind of a heuristic fit function, which tells us that there are two timescales that are depicted in this dynamics, a short time scale and a long time scale. Both can be captured by fitting these curves, which is what we have done for the red, green, orange, and blue curves over here. And we then performed Monte Carlo simulations of this pair of helium atoms in the ICD process, which I described earlier. This was what actually Keshav did to show the red and the blue ball are two different helium excited helium atoms roaming the surface of this droplet. So they then come together, and they are going to come together in about a second. They coalesce, and then the ICD process happens. Likewise, there are also, we realize, longer trajectories in which they go around like almost like deer on the IIT campus, playing their own games and whatever. But finally, they meet at some swamp, more or less, right? So, sort of giving that sort of an analogy, there's a longer trajectory to their meeting as well. So these two kinds of trajectories lead to two different time scales for the dynamics. Okay, with that, we also discern that there is the roaming times that we have here have R to the 3/2 scaling from fitting these curves, a very nice scaling result. This was indeed, in fact, published in scientific reports late last year. Okay, now I come to the final short story of this talk. I spoke about nanoplasmas being created in helium nanodroplets by intense infrared pulses interacting with them, right? So this study was performed at another free electron laser, Flash, like the superhero Flash in American comics, at Hamburg in Germany. So this is a long free electron laser which is several hundred meters long. And you can see essentially here this arc, which is the Petra ring of the synchrotron. So this, if you imagine a circle over here, underground to this is the synchrotron, which was essentially also home to this very important Nobel Prize in chemistry given to the structure of ribosomes, where Ada Yonath and Venki Ramakrishnan shared this prize. A good part of this work, especially Ada Yonath's, was actually done here at the DAISY synchrotron in Hamburg. There is a free electron laser Flash for soft X-ray wavelengths over here. This is the experimental hutch where the experiments are performed. So these have been used to image droplets and vortices in them. This is from the imaging of vortices done at the hard X-ray free electron laser in the US, LCLS. But these vortices are also observed in the other tabletop superfluid, which is Bose-Einstein condensates, which also can be in a superfluid state. With that remark, I move on, and then I will skip the details, but this is just an evidence to show that when a very intense near infrared pulse interacts with these helium droplets, it turns this ultra cold millikelvin nanoscale ball, which I call Laddu, into a very hot plasma whose temperature can be several thousands of Kelvin, indeed, almost as hot as the sun. That's the power of intense laser matter interaction, right? So why that happens is, in the beginning, the infrared pulse interacts with the matter, then it creates some free electrons. The electrons are used to heat the nanoparticles in the laser field, and after the pulse is gone, they come out. So we decided to capture the movie of this nanoplasma evolution using a free electron laser. The size of this nanoplasma is 10 nanometers. Electron microscopy will not work because it's a static technique. Of course, today, using electron pulses, again created from primary femtosecond pulses, one can also use electron pulses to do electron scattering, but it's all these are very challenging. Electron scattering itself is a very challenging experiment. So X-ray photon scattering is, in that sense, more amenable and is far better developed to study this. So in this case, the first pump pulse is intense near infrared. It crisscrosses with doped droplets, creates the nanoplasma. The intense infrared is gone. Then the intense X-ray pulse comes and interacts. The X-ray pulse is so intense that from just one femtosecond X-ray pulse with photon energies of 250 nanometers or wavelengths of 5 nanometers, from just one pulse, there are enough photons which scatter from the target and reach the detector. Okay, so that happens, and we can capture the scattering pattern on this very special single photon X-ray PNCCD detectors. So a team of researchers is often required to perform these experiments, where the facility grants a successful proposal all but a few days and few nights to complete their work. So this was quite an example of international cooperation in itself, with researchers from India all the way in Asia to the US and through Europe and so on. So quite a nice and fun effort, and it was fantastic to present this proposal and lead this experiment. So then you see in this case the ionization process, the white balls that are coming out are electrons. So they are forming, the nanoplasma is formed and it's coming out. And watch the time scale. This is happening in a better part of just few hundred femtoseconds. Can I take click? Can I take a series of images of this expanding nanoplasma? That's the question we asked, and we could with some amount of success. So pictures in this kind of diffractive imaging don't look like pictures on our mobile phones. Of course, these are diffraction images, so we get rings from this. So we can, these are similar to powder diffraction images that one obtains for condensed phase or nanoscale samples. It would be just sufficient to say that. And we have the images of neutral helium nanodroplets without the nanoplasmas being created. We see these prominent rings over here. I just want to show you that we have a distribution of nanoparticle sizes in the jet. So we have rings with different, inter-ring spacings and so on, which are well reproduced by forward-fitting simulations, which Keshav has done. But then for the nanoplasmas themselves, all the way from a delay between nearly 0 picoseconds or 0.25 picoseconds between the pump intense NIR and the probe X-ray pulses, all the way to a nanosecond, we can take snapshots, albeit of different nanoparticles appearing and reappearing again and again in the jet through the free flow, right? And we can see various nanoplasma structures coming. So in some sense, we are imaging the nanoplasma dynamics as follows: neutral cluster, ionization plus 500 femtoseconds or half a picosecond, then plus T plus 6 picoseconds, T plus then all the way up to 1 nanosecond. The diffraction patterns change and give us a picture of the dynamics following the near infrared pump ignition. So with that, we in some sense establish, not just us, there are of course a community of researchers who uses this technique to image nano, micro, and maybe even sub nanoscale objects already, in the sense of the most advanced states of photon and X-ray photon science. So in the future, we would like to exploit both angstrom, atomic, and attosecond timescales to form space-time movies, space-time dynamic, using hard X-ray free electron lasers. Again, second-grade free electron lasers spanning over several kilometers in Hamburg, or it could be also LCLS in the US, and so on. So this presents a vision for the future of this kind of science. We already did measurement at the UVX European XFEL in the leadership of Marcel Mudrich, and determined a lot of structures of these nanoparticles. These are single shot X-ray diffraction images of magnesium, SF6, oxygen, and other dopants inside helium clusters. This is work in progress. In fact, one of the technical papers is already submitted to a journal. We have composite single site, multiple site, open structures, and even foam structures that are visible in these diffraction images. With that, I would like to now sort of emphasize that there is not only plenty of room, there is plenty of room and time at the bottom. With that, I would like to thank the organizers for this opportunity and you for your attention. I will be happy to take any questions if there are.
Siva,
Yes, sir.
this is Bhaskar and I have a question.
Yes, Professor Bhaskar.
Do you hear me?
Yes, I can hear you. Can you hear me?
See, I have heard that people have produced quantized vortices in some of these helium droplets.
Yes.
So, how will your physics change? Suppose I have a helium droplet containing one quantized vortex. It brings a normal core and so on. So, will it help aid your study that you started at the beginning?
Yes, Professor Bhaskar, this is a very nice question. In fact, we do think in some of our imaging experiments, we already see impacts of these vortices, in the sense that when we dope atoms inside nanoscale superfluid helium and we have vortices, what typically happens or tends to happen, as evidenced in this experiment of performed by the group of Andrei Vilazov and colleagues, is that these dopant atoms tend to get stuck inside the vortex. I will zoom in over here. So this is a typical vortex, and xenon atoms were doped on these droplets. So xenon atoms got trapped into these vortex funnels, and the scattering pattern which they saw on the detector, which is here, the scattering is essentially scattering from the xenon atoms. These dots are from the xenon atoms, essentially, apart from the overall helium structure which is present. So we will have a different sort of nanoscale structure of the dopants inside the droplets, Professor Bhaskaran. As also is shown in these images, this was our goal also. Here, in fact, your insightful question is what we tried to perform during this beam time, where we put different atomic and molecular species in the droplet. The motivation for doping with magnesium is that there is indirect evidence from laser spectroscopy that the structure of magnesium atoms doped in helium atoms is like a foam. That is, atoms are not in some sense at the interatomic distances as they are in metallic in solid magnesium. They're actually loosely bound. There is some intermittent helium atoms also inside. A foam structure is formed. The earlier studies showed that this foam can collapse when laser excited with optical lasers. So we wanted to examine, for example, nanoplasmas formed by one intense X-ray pulse with different single and compact and multi site targets which are probed by a second X-ray pulse. So it is an X-ray pump X-ray probe experiment. The X-ray pump X-ray probe did not quite work very convincingly at some level. A part of it was maybe successful for technical reasons. However, for just imaging these droplets themselves and discerning their structures, we do see the diffraction patterns to be very, very different visually here, and therefore in its analysis also quite different. So there will be marked differences, Professor Bhaskaran, if vortices are also present.
So thank you for the fascinating presentation. Thank you.
Thank you, Professor Bhaskaran, for the nice question.
Any more
There are any,
questions?
sir? Yeah. Please go ahead, sir.
Any more question I ask? I am RO from ICSR. If there is
Yes,
no
yes.
question, we can close the session.
Yes. So if there are further questions, I'm glad to answer them. If questions arise further in the future, you could also drop me an email. We could get in touch sometime, or even better, visit us at IIT Madras. We would be glad to play host. That's very much possible too.
Thank you, Professor Ramakrishnan. Thank you for the wonderful lectures. This is a series of webinar being organized by the IIT Madras, by ICSR, as the successful completed ANRF funded projects. So thank you very much.
Thank you so much, Dr. Arumugam, and everyone in the audience.
Okay.
It's a pleasure, and I will